Here we are back again just to finish up our problems here. We're starting chapter 8. We're looking at some integral examples that we have either seen before, done before, or this one is slightly new and different. So once again, we're going to use our Pythagorean identities that are right here, and this doesn't quite match. Imagine if we took the one most like that and rearranged it, it would say 1 minus cosine squared, and we could rewrite that, but that's not what we have. So we're going to use the power of conjugates, and we're going to multiply by the conjugate of that Pythagorean identity. So we expanded it out just a little bit by multiplying by the number 1. In this case, 1 is 1 plus cosine over 1 plus cosine. This allows the denominator to finally look like that Pythagorean identity. Yeah, so that's right. The denominator is our Pythagorean identity. We can rewrite it as sine squared, and that's going to make this problem just a little bit easier now. Believe it or not, as ugly as that looks, if you take a look at some of your basic trig identities, there is a way of, once again, rewriting these so that it is rewritten in a much nicer form. Because you see, 4 divided by sine squared is the same as cosecant squared. And cosine divided by sine squared is like cosine over sine times 1 over sine. So now we're back to having some nice sort of original, regular, everyday integrals. Ta-da! And we're done with that one. So let's try one more example of review stuff. You've seen this once, and I think it's the hardest type. This one is the big mama jama. This is the one where you think to yourself, maybe I could use U substitution. But then I wrote the problem correctly. I got rid of the 1. And now you think to yourself, maybe could I try U substitution? Sorry, I copied the problem wrong. But now it's correct. Let's try it. Well, hold on a dadgum minute there. I might see if I can edit this one because I, once again, made a mistake. I'm trying to set up the problem so that it covers 3 different things. It is correct now. Let's think about what would happen if we used U substitution. Well, that doesn't quite work. It turns out that while the negative 2x would work out pretty well, this minus 2 is really throwing us off. If only we had another number that was up there. If only we had something maybe to the effect of, gosh, I don't know, maybe plus 1. This is nothing more than negative 2 times x plus 1. So that's what we're going to do. You saw an example of this before. It's called splitting the equation. Watch what happens. And by splitting, I mean adding and subtracting and then splitting. Watch what happens. Now, if we add 1 and subtract 1, which has a net gain of 0, that's going to allow us to actually write out that first integral, and we'll be able to use this same U substitution that we had here. That first integral might look something like this once was substituted. Well, now, things are looking up here. So we've at least got half of this problem right. The second half, however, looks a little more difficult. And U substitution is not going to work here. There are no x's up in the top. We know that if we just let the entire square root equal U, it's not going to work. But we did learn, if it's in the denominator, about completing the square. So maybe for the first step, what we can do is just rewrite the bottom and divide out a negative. Now we can focus on just completing the square for this little portion right here. Take half of your b value, which is 1, square it, which is still 1, and then we're going to add and subtract that number. Don't forget though, this minus sign out front means we've really subtracted 1 from this equation. So if I add 1 here, the parts in green have literally added 1 and then subtracted 1, a net gain of 0. When we clean it up, it's going to look more like that perfect square. Something to the effect of this. And if you remember your arcsines, your arctangents, and your arcsecants, this one, because it is a constant minus a variable squared, should remind you of the arcsine. And there we have our final answer. We integrate this using the power rule. We integrate this using the arcsine. Back substitute. We're all good to go. That are your challenges.